Great. Welcome everybody to this week's GOCC. Before we get started, I just want to remind everybody of our community agreements or our community guidelines. And that is that the first one is that we're all learning. So this is a learning seminar with sometimes pretty advanced topics, but we all share this love for mathematics and combinatorics that we're all willing and able to learn. So we're all learning. And the second one is that everyone has something to contribute. So please feel free to ask questions throughout the talk. Use the chat to ask those questions, and then I'll be the moderator today. And so I'll kind of jump in and ask Sophia those questions when I find appropriate timing. And the last thing is that no one has all the answers, not even the speakers. So we can think about the questions together if we don't have them, or we can, think about them after the talk. But please feel free to ask questions, and they're highly encouraged. All right, and so today I'm very pleased to have Sophia Elia here from FU Berlin, and she'll be talking to us about the congruence normality of simplicial hyperplane arrangements. So let's welcome Sophia.
Thank you. And I'm really excited to be here and meet you all. And I also really like it that you start off these seminars with the community agreement. I think that's really cool. So today I want to talk about some recent work that I've been doing with Michael Kuntz and Jean-Philippe Lebet, studying simplicial arrangements, and in particular, if they have a certain property called congruence normality. So an outline of the talk, I want to start off with what are simplicial hyperplane arrangements and go through some of the background and history. So in particular, there's a catalog of simplicial arrangements in rank 3, which has been evolving over the last 50 years. And I want to talk about what's known and what's not known. There are a lot of really interesting open problems there. And so this list, it's not known whether it's complete or not. And what we'd like to do is investigate it some more and add some more structure to it. In particular, we want to verify which of these arrangements have this property called congruence normality. So in the second part of the talk, I want to talk more about congruence normality, tell you what it is, and tell you about our approach to verifying when an arrangement has the property of congruence normality. And to do that, we're going to use oriented matroids. So that'll be the second part of the talk. And then in the third part of the talk, we'll look at the results. So we'll see which of these simplicial arrangements actually have this property. Yeah, so that's the plan. So let's start off with some definitions so that everybody's on the same page. So we're working in a real vector space of dimension D, and we're going to look at hyperplanes, which are just subspaces of codimension 1, and we want them all to contain the origin. So what you can think of is just the set of points in a real vector space that are orthogonal with respect to the usual dot product to some vector. And then a hyperplane arrangement is just going to be a set of hyperplanes, a finite set of hyperplanes. To tell you what a simplicial hyperplane arrangement is, we have to talk about the regions. So if you look at the complement of the arrangement in your space, it breaks up the space into connected components. And the closures of each of these connected components are going to be the regions of the arrangement. A region is going to be called simplicial if each of the normal vectors to its facet defining hyperplanes, if that set is linearly independent.
Sophia,
and then
we have a question.
Okay.
So Galen asks, are the hyperplanes distinct, or do we allow multi-arrangements?
Distinct. Sorry, I should have said that. Okay, I wanted to ask another side question. I keep hearing the doorbell sound. Is that Is that normal? I don't know if you can all hear that.
Well, we can hear it. It's people coming in, but I think this is the first time that I'm hearing it in our talk. So Alex, I don't know if you can change that setting. But yeah,
But
that just means more people are coming in.
It's not a big deal, but I was just wondering if it was like you could turn it off or something.
Yeah, no, we'll try to turn it off.
Okay. Right, so a simplicial arrangement, an arrangement is simplicial if every region is simplicial. And then the rank of the arrangement is the dimension of the span, the linear span of the normals to the hyperplanes in the arrangement. Okay, so that was a lot of definitions pretty quickly. Are there any more questions before I go on? No? Okay. Okay, so in 1971, Grunbaum published a catalog of rank 3 simplicial arrangements. So these are planes in a 3-dimensional vector space, but you can also think about them as arrangements of lines in a projective plane. So it turns out that there are 3 infinite families of simplicial arrangements, and then 90 other sporadic arrangements. And the 3 infinite families are in this picture here. So the first family is the family of near pencils. And these are arrangements of lines so that all of the lines except for one share a common intersection point. And the second family is made up of regular polygons and their lines of symmetries. So the hyperplanes are going to be the facet defining hyperplanes for each of the edges of the polygon, and then each of the lines of mere symmetry. And the third family comes from even polygons, where you do the same construction. You take each of the hyperplanes from the edges, and then you take the lines of mere symmetry, but you also add the line at infinity. So we have to think in the projective plane here, but each of the regions here is a triangle, and that's how you see that these arrangements are all simplicial. Okay, so there are these 3 infinite families of arrangements, but there are also these other 90 arrangements, and it's when Grunbaum originally published this catalog in 1971. He conjectured that this list was complete, and since then there have been a few changes, but overall it's really remained very close to what we know now. But it's still not known if these are the only sporadic arrangements, and even if this list is finite. The number of hyperplanes in these arrangements range from 7 to 37. And again, it's not known if 37 is a true upper bound, or why that's an upper bound, or like where many of these, like what is the origin story for many of these arrangements. So I got these pictures from an updated version of the catalog, which really only had like 2 amendments that Grunbaum published in 2009. And that's a really cool paper. I mean, it's beautiful. I love looking at these different arrangements. I think they're so cool. So I would encourage you to look at that. It's called A Catalog of Simplicial Arrangements in the Real Projective Plane, if you're curious and you haven't seen it before.
Sophia, Mark asks, all of these are full rank. Can I take out the bar from the near pencil arrangement and still be simplicial?
That's a good question. I don't think so, because, all right, so then, right, they're full rank. So we're talking here about arrangements of rank 3, right? So if you took out, sorry to keep flipping back and forth, I know that's disorienting, but if you took out this, I guess if you took out the one line which is not contained in this, does not have this intersection point, then you could drop the rank, and then you would have a rank 2 arrangement. And I think it would be, off the top of my head, I'm not sure, but I think it would be simplicial. Yeah. But if you, yeah, you'd have to take out that line for it to drop rank, because otherwise you would still, like that's how you generate the family. You just keep adding more lines that go through this special intersection point. Okay, yeah. Sorry, I'd have to think about it a little. I think it would still be simplicial, but I'd have to think about it a little bit more. Okay, so since then, since 2009, a few more arrangements, 5 new arrangements have been discovered. 4 of them were discovered by Kuntz in 2011, and 1 more was discovered earlier this year. And in the one that was discovered earlier this year, Kuntz actually came up with a greedy algorithm to generate these simplicial arrangements. And that greedy algorithm quickly recovered all of the known simplicial arrangements and this 1 more new one. But it's still just a conjecture, like is this list now complete? Also in 2011, in that same work, Kuntz proved that the list is complete for up to 27 hyperplanes. And in other work, Kuntz and Heckenberger have been investigating Weyl groupoids, which are generalizations of Weyl groups. And these groupoids lead to a larger family of simplicial arrangements, which in particular include the simplicial arrangements from Weyl groups. And they constitute a pretty large family of the sporadic arrangements, like 53 out of what's now 95. So this is cool because it gives like an algebraic motivation or origin story for some of these simplicial arrangements. It gives an explanation. Yeah, it's still not known like why for sure if 37 is an upper bound for the number of hyperplanes. Okay. So here's a little advertisement. In our article, we're going to, for the updated catalog, give the normals and invariants to all of the known sporadic arrangements. And this is work of Michael Kuntz. And what he did actually was take this PDF of Grunbaum and code something to scan it and come up with all the normals. And then restrict to subarrangements of those arrangements and see if they're still simplicial. So that's pretty cool. And now if you're interested in simplicial arrangements and you'd like to go play with them, you can take these normals and put them in Sage like we did, or whatever you'd like to use. Okay, so the rest of the goal is to add a little bit more structure to this catalog of known simplicial arrangements. But we want our approach to, yeah, so we'd like to add a little bit more structure, and what we're going to do is test these arrangements for a property called congruence normality. So I'll get into that in a minute. But to do it, I sort of have to tell you about how we can get a poset from a hyperplane arrangement, because congruence normality is really a property of a poset, or actually a lattice. So what we do is, in our arrangement, we choose one of the regions, which is going to be the base region. And then we take all the other normals from the hyperplanes and we orient them away from the base region. And one way that you could verify this is just by taking the dot product with any vector in the base region and a normal of the hyperplane. And that dot product is now going to be less than or equal to 0. So we pick a region, we orient the normals away. Now, what we're going to do is to every region, we're going to assign a set of the hyperplanes. This is called the separating set, aptly, because what it is it's the set of hyperplanes that separate this region from the base region. Again, like a hyperplane divides your vector space into 2. And so now you're just checking if your region lies on the same side as the base region. And again, this is something that you can verify by taking a vector inside of the region and taking a dot product with the normal to the hyperplane. So now we create a poset, and the elements are the regions, and we have an ordering given by one region is less than or equal to another if you have a containment of the separating sets. Okay, so we'll see an example on the next slide, but I thought I would pause now and ask if there are any questions about that. Doesn't look like it. Okay. All right, so here's actually a rank 2 arrangement, which you might recognize as A2. It has 3 hyperplanes, and actually no matter which base region you choose, you'll get this hexagonal poset of regions. So now we want to ask the question, when you have a poset of regions of a hyperplane arrangement, what do you know about this poset? What order theoretic properties can you determine? And there are some things that are known. So if you have a simplicial arrangement, then actually the poset of regions is going to be a lattice for all choices of base region. This was proved in 1990 by Bjorner, Edelman, and Ziegler, where they also showed some other properties. But here, this was sort of a special property of a Coxeter arrangement, that it didn't matter which region we chose before we were going to create the base region. In general, if you have a simplicial arrangement, you'll get non-isomorphic posets if you choose different base regions. So you can know other things for simplicial arrangements, like you'll know that the lattice of regions is actually semi-distributive. But again, touching on the specialness of the Coxeter case, for Coxeter arrangements, which if you don't know what that is, it's a subfamily, a nice subfamily of simplicial arrangements that their symmetries are really interesting. I should have a better explanation than that, but yeah, so they're a subfamily, a really special subfamily of simplicial arrangements. And it turns out that the poset of regions of finite Coxeter arrangements are always congruence normal. This is a result from 2004. So this fact leads you to the question, since we now have a subset of the simplicial arrangements, a nice subfamily, how far does that extend? Are all simplicial arrangements congruence normal? Is this the largest family that has that property, or is there another family such that the posets of regions are congruence normal? So already this is sort of leading us to investigate this property. And now let me actually tell you what this property is. So a subset of a poset is convex if for any 2 elements in that subset, the interval between those 2 elements is contained in the subset. And a lattice is congruence normal if it's obtainable from the 1 element lattice by a finite sequence of something called doublings of convex sets. So let me describe what that is. Here we have a picture of a sequence of doublings from a 1 element lattice to the hexagonal lattice that we just saw. So what you do is you take your subset S, and you're going to create 2 copies of it within your poset. So you'll take one of the copies of S, and all of the elements in the poset that are greater than or equal to S, and you'll place it at height 1. And then you'll take your second copy of S and all of the other elements of your poset and place it at height 0. So now your elements have 2 coordinates, and the relation is given by one element is less than another if you have the less than or equal to in both coordinates. So let me explain that with this example here. So here we're going to take our convex subset to be actually the whole interval, and we're going to double it. So we're going to create two copies. We put one copy at height 1 and one copy at height 0, and then we have to add in these additional two relations because this element is less than or equal to itself, and it's also in the second coordinate, like this is at height 0 and this is at height 1. But we don't get anything here. Okay? Right. So there's a related property to congruence normality called congruence uniformity. And it's a stronger property normally because instead of looking at convex sets, we just allow intervals, doublings of intervals. But it turns out that for simplicial arrangements, congruence normal is actually equivalent to congruence uniform. So in what follows, I'll just sort of use them interchangeably. Okay, I feel like this is a good place to pause and ask for questions again. Because, yeah, this is sort of the main definition.
I have a question. Can you explain how to go from the third to the fourth picture with it?
Well, if something pops up, I guess you'll let me know. Okay.
Sophia.
Right. So we already saw that congruence normality sort of arises as it would be nice to know for which simplicial arrangements are congruence normal.
Yeah.
Yeah.
I think your internet cut off real quick.
Okay.
And so Mario actually had a question. Mario, do you want to ask it again?
Yeah, I was just wondering, can you hear me?
Yes.
Okay, yeah, that wasn't my question. Also on the previous slide, can you explain how to go from the third to the fourth picture with a doubling?
Yeah, so you're gonna take these two elements as your convex set. So then each of, like this one will get split into this interval, and this one will get split into that interval. And then you see that like this element was greater than both of those, so it sort of gets carried along upstairs. And this element is going to be in the complement, so it stays downstairs.
Ah, I see. Thanks.
Yeah, thank you for asking. Okay, hopefully my internet will hold out. All right, so I wanted to give a little bit more motivation for studying this property. And that's because congruence uniformity and normality, when a post set of regions has this property, it means that it's well behaved in a certain sense. And that sense is that it's easier to understand its lattice congruences. And the reason that you would care about that is that when you start to talk about congruences on post sets of regions, you start to hit really beloved subjects in combinatorics like the permutahedron and the associahedron. And the reason for that is that a simplicial arrangement is the normal fan of a simple zonotope. So for example, you could ask a question like, if I have a simplicial arrangement and I start to glue the cones together of that arrangement in a nice way, do I still have the normal fan of a polytope? And there's been a lot of interesting recent progress on this. In 2019, Pilo and Santos put out a paper called quotient topes that said that in type A, or this is possible, and they gave a construction for the polytope. And then recently in July, Pilo, Pedrol, and Ritter looked at type B, and they showed that in the nice case when under a congruence, I'm using some words that I haven't really explained, but I'm about to. Your shards admit a shard polytope, then you can construct the polytope of this quotient fan. And they conjecture that if your post set of regions is congruence uniform, then you're in this nice situation where you can construct the polytope. So this is just to give some more motivation for, to show that congruence uniformity is a property that pops up, and also that in order to make this conjecture, to address this conjecture, it will be nice to know which of the simplicial arrangements are actually congruence uniform. Yeah, so this is just some more motivation for studying congruence normality. So now I wanted to sort of summarize what we've done up to this point. So we discussed the current catalog of simplicial rank 3 hyperplane arrangements. And one of our goals is to figure out which ones are congruence normal. So now we know what that actually means. It means it's obtainable by a finite sequence of doublings. And we saw some motivation for looking at this property. But this sequence of doublings is not how we're going to approach verifying which of these arrangements are congruence normal. Now I want to talk about our approach. So our starting off point is going to be these pieces of hyperplanes called shards. And this was introduced by Reading in 2003. So I'm going to walk us through how to get the shards of an arrangement. So here we see an arrangement of 10 hyperplanes. Actually, this is one of the arrangements from those infinite families. It's shown via stereographic projection, but you can see that it's coming from a pentagon and its lines of mere symmetry. And I've already selected a base region right here that's marked with a dot. Okay, so to create the shards somehow shards are going to give us congruence normality. So let's see how you create them. What you do first is you choose a place where at least 3 hyperplanes intersect. So I'm going to choose the center here where all of the straight lines intersect. And then I restrict to this subarrangement. So I forget about all of the other hyperplanes. And then I see which unique region in the subarrangement contains my original base region. And in this case, it's this region here, which is bounded by the pink and the black hyperplane. These become something called the basic hyperplanes. They're the bounding hyperplanes of the new basic region. So then what we do is all of the other hyperplanes that contain this intersection point, we split them into 2 pieces. We cut them. So the red, the orange, and the blue hyperplane get cut. And now we go through and we do this for every single place where at least 3 hyperplanes intersect, and it gives us the shards of the arrangement. So I know that that's kind of a quick verbal story. Does it make sense, or should I maybe repeat something? Maybe you can give me a nod or something. Okay, cool. Thanks. Okay, so now we know how to get shards. So how do shards tell us if a post set of regions is congruence normal? Right. So we're going to create a directed graph on the shards. And one shard is going to have an arrow to another shard if 2 different criterion are fulfilled. The first one is that the unique hyperplane that contains a shard, for example, this red shard is on this red line, it has to cut the hyperplane that contains the other shard. So for example, the red line cuts the green circle. And then the second criterion is that the shards actually, so the shards are actually like the closures of these pieces of hyperplanes. And you need that the dimension of intersection is codimension 2.
Sophia?
So in, in this picture. Yeah.
Sorry.
Yeah.
Could I interrupt you? With Cyrus had a question, just back to the picture. Can you just quickly like explain again how to read the diagram, and just like how does a hyperplane get sent to a line or curve in the diagram?
Oh yeah. So right. So this is a stereographic projection, which means, and I'm choosing it so that I get as much symmetry when I draw this as possible. So what you should imagine here is that so actually think of a pentagon at height 1, right? Maybe, well, just think of a pentagon first. I don't know if I want it at height 1. And so I have all the edges of the pentagon, and then I have the lines of mere symmetry, which are vertical. And now what I'm going to do is my perspective point for my stereographic projection is going to be like right on this line that contains all of those lines of mere symmetry. And that means that when I do my stereographic projection, those lines of mere symmetry are going to get sent to straight lines. And the other hyperplanes, which are edges, are going to end up being like great circles, like arcs on the plane. So that's how you get the picture. It would maybe be a little bit easier to understand what's happening in this picture if you just had all circles, but then you would lose some of the symmetry. Should I explain the shards again, or
Maybe
is that
quickly.
okay? So let's look at another example. Let's take what happens around this point. Okay, so we've got 3 hyperplanes intersecting. That's good. And so we're going to try to forget about all the other hyperplanes. And now we have to see which region contains the base region. And so if you follow my cursor, it's going to be this region right here. And the 2 hyperplanes that bound that region are this black circle and this purple circle. That means that the blue hyperplane has to get cut. So all I do to create the shards is I go around and I do that for every single intersection point, where at least 3 things intersect. Yeah, great. Okay, so now what we're doing is, in order to check, this is all about how can we check for congruence normality. And we're going to create a directed graph on shards. And it turns out that if this directed graph is acyclic, then it means that our post set of regions is congruence normal. So the conditions were that one hyperplane has to cut another one, and also the 2 shards actually have to intersect. In this picture, it means that the 2 shards intersect at a point. I mean, if you imagined like the closures of these lines. So you can see here that we do have a cycle in the shards here, right? The red one is cutting the green one, is cutting the orange one, is cutting the blue one, is cutting the red one. So this is a simplicial hyperplane arrangement such that with respect to this base region, the post set of regions is not congruence normal. And actually, this is the smallest example of a not congruence normal arrangement, simplicial arrangement in rank 3. Okay, so this is a geometric criterion, but we want to approach it from an oriented matroid perspective. And the reason that we want to do that is because once you start to have a lot of hyperplanes, it can get really hard to compute things if you're working with geometric objects. So the number of regions grows exponentially with the number of hyperplanes. And this means that you don't want to end up actually computing the post sets of regions themselves. Like, so you wouldn't want to check if, you wouldn't want to have to create a post set of regions to check if it's constructible by doublings. And also checking geometrically intersections of shards ends up kind of recursively requiring to calculate posetsets of regions, and yeah, calculating polyhedral objects and dimensions of intersection can also be sort of expensive or something. And the idea is that if we work from an oriented matroid perspective, we'll have a more compact way, combinatorial compact way to encode this information. Okay, so the idea is to take those shards and record them as covectors in the oriented matroid from the hyperplane arrangement. So if we have an ordered set of vectors, in this case, it's going to be the set of normals to the hyperplanes in the arrangement. A covector on that set is a vector of signs, like 0 plus or minus, such that we just take a chosen vector and we take the dot product with each of the vectors in our set, in this case, the normals, and we record the signs. So this is going to give us a lot of geometric information about the arrangement, because if coordinate I, for example, is 0, it means that that vector that we chose has to actually be on hyperplane I. If it's negative, it means that we have to be on the same side as the base region of hyperplane I, and so on. So like, you really, in a compact way, you express a lot of information about the geometry here. So in order to record shards, we'll actually not want to keep track of all of the signs. We just care about a subset of the normals and the sign patterns on the normals. So if you have a subset that you care about, then a restricted covector just puts stars in all of the entries that aren't in that subset. Okay. So to encode shards as shard covectors, a shard covector is a restricted covector with exactly 1, 0. And I'm going to tell you how to read off the shard covector from an arrangement. So this is actually the arrangement A3. It has 6 hyperplanes, and I've chosen a base region again. And I want to focus on this shard here, which I've marked with a theta, that lies on hyperplane 6. So the first thing that we want to do is figure out which hyperplanes do we not care about, which coordinates are we going to throw away. And to do that, I go around and I see which hyperplanes do not cut the hyperplane that my shard lies on. So if I go around, I see, oh, hyperplane 1 and hyperplane 5 cut hyperplane 6. I keep going, I see, oh, 3 and 4 cut hyperplane 6. Ah, but 2, where is that intersection? Here. 2 doesn't cut hyperplane 6. And this means that I don't care about hyperplane 2. I'm going to put a star in that entry in the covector. And the reason is, well, points in this shard lie on both sides of hyperplane 2. And that's really what I'm recording here. So then if I look in the first coordinate, oh, the covector tells me that I should be on the opposite side of hyperplane 1 as the base region is, because it's a plus. So here's my base region, and you can see that if I want to get to the shard, I'm going to have to pass through hyperplane 1. So that's how shard covectors capture the information of a shard, and actually we prove that really they're in bijection. You can really record the information of a shard with just this pattern of signs, plus, minuses, zeros, and stars. Okay. So now we've got the shards, but we still need the cycles. And to do this, we need 2 more notions, and then we can present the theorem. So first of all, what we do is we look at the point configuration associated to the hyperplane arrangement. So remember that we took all the normals and we pointed them away from the base region. So to get to a point configuration, what we do is we just take those normals and we intersect them with the hyperplane. And in rank 3, this means now that we have a configuration of points actually in the plane. So a line, as you might guess, is just a subset of the points which correspond to the normal vectors, which lie on the line. From there, we're going to look at these covectors which come from the lines of our arrangement. So first of all, we take a line which is spanned by 2 points in the arrangement. And then we take a covector, which is going to record the sign patterns of all of the points in the arrangement with respect to that line. So, for example, if I looked at the line spanned by 0.1, 0.5, and 0.6, a covector would be like a 0 in this entry, maybe a plus in this entry, a minus in that entry, a plus, a 0, and a 0. So it's just a covector that's 0 exactly on that line. That's kind of fast, but I feel like I'm running out of time, so I should keep going. Okay, so then one more operation is the intersection operation. And what you do is for 2 covectors, you're going to compare them coordinate-wise. And if the signs disagree, then you're going to replace the entry with a 0. And if anything is a 0, then it's going to get replaced with the 0. So it's sort of absorbing in some way. And then stars are going to act like identities. And what this is really doing is when you're comparing 2 covectors, if you have a plus in one entry and a minus in the other, it means that those 2 points lie on opposite sides of a hyperplane. So what we want to say is that like their intersection is going to have to be on the hyperplane. Okay, so then what we can show is that you have an arrow between 2 shards if and only if the first condition corresponds to this cutting of hyperplanes. One of the covectors has a plus or a minus in the appropriate coordinate. And also, there exists a line covector such that if you take that covector and intersect it with the 2 shard covectors, you get the line covector back out. And this is encoding the part of the dimension of the intersection criterion. So what's nice about this is that we've taken a geometric criterion and we've turned it into take your covectors and compare their coordinates basically and check for entries in certain coordinates. So this is sort of an efficient way to check for congruence normality. Okay, so now, are there any questions? I think this is a good place to pause. I know I went through that really quickly. Okay, so, but I do want to share with you the results from the computation. So what we did was we then checked all.
Sophia, I guess I do have a question. So can you go back to the last slide? You said that encoding this is more efficient, or I mean, now we have an efficient way to encode this. And so now that you're going to talk about computational results, does this help you with any of these computations?
Yeah, definitely.
Okay.
So what we did for the computations is for each of the hyperplane arrangements, we generated the co-circuits of the oriented matroid. And we generated these shard covectors and these hyperplane and these like line covectors. This is the most, like generating these things is the most computationally expensive part of it. But it's not exponential. And then really like the perk of this approach is that Now to check for congruence normality, we really just have to do like checking values of entries and comparing coordinate-wise the covectors. So yeah, that's like, when I say that we check the list for rank 3, we're really going through, and for every hyperplane arrangement, we're generating these things, and for every choice of base region, we're checking if there's a cycle in the shard digraph by using this method. Yeah?
Yeah, thanks.
Okay, cool. Right, so this arrangement is like a blown up image of the new arrangement with 35 hyperplanes that Kunz found earlier this year, and it's one of our special arrangements that I want to talk about. So we took this list. The list that we checked had 119 different arrangements in it. 95 of them were sporadic, and we split it up into 3 categories. Those arrangements which are always congruence normal, sometimes congruence normal, and never congruence normal. And I'm going to tell you a little bit more detail about each of these, but in particular, I want to point out these 5 exceptional cases that we found, which are really interesting, I think. And yeah, as we go along, I'll sort of say why that is. So let's look at the case of always congruence normal. This means that it doesn't matter which choice of base region you have, the post set will always be congruence normal. So near pencils are always congruence normal because all of the lines intersect in one point. So any path in the shard digraph has at most length 1, so you can't get a cycle. And then the other interesting result here is that finite vowel groupoids of rank 3 are always congruence normal. So remember how we said that there was this result from 2004 that Coxeter arrangements are always congruence normal. Well, finite vowel groupoids generalize this family, and it turns out that actually they're also always congruence normal. So that's pretty cool. But then very mysteriously, there are these 2 other arrangements. So that makes you wonder what's really going on here. And also moving forward, like, it'll be really cool to see if someone is able to prove that part of this list or all of this list is actually a complete classification of simplicial arrangements in rank 3. And so you might wonder, like, oh, could you prove that this part of the list is complete? The arrangements that are always congruence normal, or sometimes or never. So I think that's one of the reasons that it's nice to have this structure to it. There are also the arrangements which are sometimes congruence normal. This means that there is a choice of region such that the post set is congruence normal, but there's also a choice so that it's not congruence normal. And as long as these include the 2 infinite families, as long as you have big enough polygons. So in the second family, as soon as you have a pentagon, this is the case. This is the arrangement that we looked at in more detail. And in the third infinite family, you need to go from, an octagon. And then there are these 41 other sporadic arrangements that are sometimes congruence normal. And then there are 3 arrangements that are never congruence normal. And you saw the picture of the one with 35 hyperplanes. It's the one that was just found this year. And there are 2 other arrangements. So it would be really cool to understand more about these arrangements and why they're never congruence normal. Okay. Thank you.
Awesome, nice talk. Are there any questions for Sophia?
I have a question. So this might be tangential to your project, but this covector, this like sort of partial covector, restricted covector presentation is really cool. And I'm curious if you guys have developed some notion of a circle product for these restricted covectors. So I'm not sure if you've seen it, but there's like this theory of BHR random walks where you like ping chambers at each other and you do a product on covectors to sort of move around the chambers. And I'm curious, and you can do that using covectors. And I'm wondering if you guys can do that with your restricted covectors as well and get like a random walk on shards.
Oh, that sounds really cool. No, we haven't looked at anything like that yet.
Okay.
But that's what did you call it again? Circle product?
Yeah, that's, or a composition product.
Mm-hmm.
I can send you an email about it if that's easier.
Yeah, that would be great.
Okay, cool. I would love to see that.
Are there any other questions?
I also had a question. So looking at your initial shard diagrams, they looked very similar to knot diagrams, with of course the problem that you actually had, two hyperplanes are intersecting each other and then there's just the one shard that's going under. And so I'm wondering, have people like looked into, is there a connection with knot theory here?
I've never heard of that. But yeah.
Because the creation of the cyclic shard looks a lot like, you've kind of tied a knot such that you can't lift it nicely. You've got, your four squares on the box that make themselves solid. And so I was wondering if perhaps there was some deeper topological reason why this was a problem.
Well, you're probably right about that. Once you start studying, getting into oriented matroids, it becomes topological pretty quickly, and you start looking at pseudo-line arrangements and when you look at realization spaces and stuff. I haven't looked into that so much, but yeah, I bet that you're right that there's something deeper going on there.
Sure, thank you.
Any other questions for Sophia? No, I don't see any.
Hi, this is Seth. I guess a wild question would be a natural question, but maybe kind of wild. What happens if you, go beyond hyperplane arrangements and go to general rank 3 oriented matroids, the non-representable ones?
Yeah, that's a really interesting question. Actually, so as far as the shard covectors go, you can actually obtain a shard covector just with the information of the oriented matroid, which, I mean, I just started thinking about this recently, but I'm really curious to see, like, if maybe there's something that you can, more general, say, just in the setting of oriented matroids, but I haven't really looked into it yet.
Well, of course, you could, deploy the same geometric intuition by means of the, topologically, the pseudosphere arrangement, characterization of oriented matroids.
Yeah. Yeah, that would be a nice direction to explore some more. Thanks for pointing that out.
Awesome. So before we thank Sophia one more time, let me invite you all again to GOCC next week. So next week we'll have Daniel Tamayo Jimenez from Université Paris-Saclay, which was my horrible French. But yeah, but he'll be talking to us about perimetry sorting, pattern avoidance, and automata. So please join us next week for that nice talk. But yeah, let's thank Sophia again for that lovely talk. Thanks, Sophia.
Also,
All
something
right.
else next week is we have the job thing.
Oh,
is that Thursday of next week,
that's
right?
Thursday of next week. Yeah, that's right.
Yeah, so that we have some people who got academic jobs recently who are going to tell us the secrets they use to get those jobs. So anyone who is on the job market or will be at some point or isn't and just wants to come by, you're all welcome. And soon we'll send out a thing looking for questions that you might have to ask.
Yeah, and so yeah, just to kind of reiterate what Alex said. So that's September 24th, which is Thursday of next week, from 4 to 5 p.m. Eastern. And again, it's a job talk. An academic job panel. And so we'll have Sunita Chapuri, who is a postdoc at Michigan, and Chris who's a postdoc at Stanford, and Bennett Goigner, who's a postdoc at Washington, and then Julie Vega, who is an assistant professor at Kennesaw State. And so they, like Alex said, they'll share their secrets so that we can all successfully get jobs. But yeah, I guess this is a good point to stop recording.